Okay, let's do some more Lewis dot structures, and this time we'll go through and talk about the hybrids that they have as well. So, normal way to start, we start with a skeleton. Different goes in the middle. We count valence electrons. Phosphorus has 5, bromine 7. It gives us 26. When I put the rest of the electrons on here, remember I already have 2, 4, 6. When I put the rest on here, I start on the outside atoms first. Okay, then I check and see how many I have. I've got my octets for my outside atoms. That's 24. So I have 2 more. When I have more, I put them on the central atom. Then I should check and make sure my central atom has an octet, and it does. If it doesn't, I would be making a double bond. It doesn't, so we're good. So we're done. Let's go ahead and do our geometry like we normally would do. So how many electron groups? There are 4. The electron geometry. Tetrahedral. So this is that shape that you have like this. Oops, except ours has a lone pair up here, doesn't it? So the molecular geometry. So what's left is a little pyramid, but with a triangular bottom. Trigonal, pyramidal is our geometry. Okay, what else can we answer about this one? Is it polar or non-polar? So look at our geometry. It's not all balanced. It has like one end that's different. And technically it's that it has like a negative end and an end that's more positive. But anyway, you can tell that it's not balanced as far as the bonds and the atom type. So this is polar. Just so that we're clear, if we had another atom up here that was the same, then it would be nonpolar. But because it's not balanced like that, it's polar. Okay, now let's talk about our new part, and that is the hybrid orbitals. So for the hybrid orbitals, we're always going to be looking at the central atom again. And you start with the number of electron groups. I have 4 electron groups. Therefore, I have 4 hybrid orbitals. And if I have 4, what is that hybrid orbital going to be called? Well, remember that we have an order we have to go in. This is the order. So what I do to figure out what kind of hybrid orbital I have is I go through these and see what I have to get up to 4. Looking at the exponents, this one has 2, this one has 3, this one has 4. So it's sp3 orbitals. Let's try another one. We're going to start with our different in the middle. I need to count my valence electrons. Xenon has 8. Chlorine 7, that gives me 36 valence electrons. The rule is I start by putting them on the outside atoms first and make sure those have their octet. Then those all have an octet, so let's count and see. Looks like I only have 32 on there already, so I've got 4 more. And I can see that xenon doesn't really need any more, but that's too bad. I have 2 more. The central atom gets them, so I'm going to just do them out at an angle like that. And so let's do our geometry. So how many electron groups? A group is a lone pair or a bond. So this has 6 groups. So the electron geometry with 6 groups is going to be octahedral. Octahedral is the shape that's kind of a square with 1 up and 1 down. On this one, so here's our central atom. On this one I have 2 lone pairs, and on this one with the square, the lone pairs are on the top and the bottom. On the triangle, they're on the triangle, but on the square keeps the atoms. So this is how it will look. So the molecular geometry, the square is square, planar, because it's flat. Is it polar? Now this one's kind of different because, you know, if it had an atom on every spot, it would be nonpolar. But this one, it does have some differences, but they're opposite each other. And so those two kind of cancel out. And then in a way you can think about these 4 canceling as well. So its symmetry causes it to be nonpolar. Let's look at the type of hybrid orbital. Looking at my central atom, it has 6 electron groups. That means it has 6 hybrid orbitals. And so let's look at our order that we had up here. To get to 6, again, looking at the exponents, I have to, oops, looks like I'm missing one, aren't I? This should be a D2. Because to get to 6, I have to go all the way to there, sp3d2. And I can tell these exponents are the number of okay, that's all we can do with that one.